5 basic types of gas metal arc transfer methods will be reviewed. First are the 3 traditional constant voltage or CV processes: the short-circuiting process, globular transfer, and axial spray arc. The 4th and 5th modes of transfer are higher-level technology transfers, surface tension transfer, and power wave pulsed arc transfer. Both are further enhanced by waveform control technology. Waveform control technology controls every aspect of the output waveform. First, a high-speed control delivers the ideal instantaneous welding output. Each weld is made up of individual droplets of weld metal. The high-speed control regulates the development and transfer of each droplet. The second control, the slower speed control, adapts the wave shape to maintain the proper arc length. Let's look at the characteristics of the 5 major metal transfer processes in greater detail, starting with short-circuiting transfer. Short arc has the lowest heat input, making it a very fast-follow process. The weld puddle freezes quickly to allow efficient out-of-position welding. Equipment for this process is relatively inexpensive, but the short-circuit process produces some spatter, has low deposition rates, and lack of fusion is not uncommon. Here is a close-up of the short-circuiting process. There's some spatter, a little bit of violence associated with the arc. The crisp buzzing sound is caused by periodic short circuits. By using high-speed photography, you can actually see droplets forming on the end of the electrode. Current is applied, the droplet pinched off, and transferred into the puddle. Spatter occurs when the shorting is not done perfectly or there is interference to the puddle. Spatter balls can pop out of the very violent puddle as it oscillates. Globular transfer uses higher energy levels than short arc and higher wire feed speeds. This process offers a very fast follow or high speed characteristics, high deposition rates, and very good penetration. However, when viewed up close, globular transfer exhibits extreme violence in the arc. The violence of the process is shown by the large droplet size. The arc is not forming anywhere on the droplet. A current density high enough to pinch off the droplet cannot be reached. Gravity and uncontrolled electrical magnetic fields dominate this transfer method. A droplet often wields around in space as it is pushed by the arc from one point to another. You will see violent explosions as the arc actually shorts out. The current rises high to try to pinch the droplet off, but fusion occurs and the very large droplet is thrown out of the weld zone. This violence in the process accounts for the excessive spatter. The operating range of the globular transfer method is very wide. When we increase the energy levels above globular and short arc, spray arc occurs. The spray arc transfer mode offers a very stable arc and is typically spatter-free. This is normally used on heavier plate. Advantages include high deposition, fast fill, and very deep penetration. Many metals can be welded by spray arc, including steel, alloys, aluminum, and copper. However, highly inert gases such as argon and helium must dominate shielding gas mixtures. High heat input is required for the spray transfer. Because the weld puddle is large and fluid, the process can only be used for flat or horizontal welding. Due to higher heat inputs, spray arcs can cause undercutting. The spray arc process has a very controlled, stable arc. There's little spatter, minimal shorting. Molten metal streams from the electrode end. The magnetic field from the arc surrounds the wire. The high magnetic force from that field pinches the wire down at the end. Molten droplets stream through the arc to the workpiece.